Black holes. Just the name evokes a sense of mystery and awe. These enigmatic entities have fascinated scientists and the general public alike for decades. They are cosmic objects of immense density, where gravity reigns supreme, warping the fabric of space and time around them. This warping effect is so intense that it can bend light and distort the appearance of objects behind them. Imagine a place where the rules of physics as we know them break down, where even light, the fastest thing in the universe, cannot escape. This boundary, known as the event horizon, marks the point of no return. These celestial objects are not cosmic vacuum cleaners, as they are often portrayed. They don't roam the universe sucking up everything in their path. Instead, they are remnants of massive stars, collapsed under their own gravity at the end of their life cycle. When a star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. They lurk throughout the universe, from the hearts of galaxies to the vast emptiness of interstellar space. Supermassive black holes, millions to billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. What would happen if we were to approach one of these cosmic abysses? The gravitational forces would stretch and compress objects in a process known as spaghettification. The answer, as we are beginning to understand, is a mind-boggling blend of scientific theory and captivating speculation. Theories range from the possibility of wormholes to the idea of black holes being gateways to other universes. The journey towards a black hole is a one-way trip. Once you cross the event horizon, the gravitational pull becomes so strong that escape is impossible. Once you cross a certain threshold called the event horizon, there is no turning back. Time and space as we know them cease to exist in their familiar forms. But what awaits beyond this point of no return? The singularity at the center of a black hole is a place where densities become infinite and the laws of physics break down. Is it utter destruction, or could it be a gateway to something else entirely? The mysteries of black holes continue to captivate our imagination and drive scientific inquiry. To comprehend the bizarre fate that awaits an object falling into a black hole, we must first grasp the fundamental force at play: gravity. Gravity is the invisible hand that shapes the cosmos, governing the motion of planets, stars, and galaxies. It is the force that binds us to the Earth and orchestrates the dance of celestial bodies in the vast expanse of space. Gravity, as we experience it on Earth, is a relatively weak force. Despite its weakness, it is the reason why we stay grounded and why objects fall when dropped. Jump, and you come back down. This is because Earth's gravity pulls you back towards its center. Throw a ball, and it eventually falls back to the ground. The force of gravity ensures that what goes up must come down. But near a black hole, gravity becomes an irresistible titan. Its strength is so immense that it can trap even light, the fastest thing in the universe. Its pull is so intense that it distorts the very fabric of space and time. Imagine a trampoline stretched tight. If you place a bowling ball in the center, it creates a dip. This dip represents the warping of space-time caused by a massive object. Now roll a marble across the trampoline. The marble represents an object moving through space. As it nears the bowling ball, its path curves, drawn towards the heavier object. This is similar to how gravity bends the path of objects in space. This is a simplified analogy for how gravity works. The trampoline represents the fabric of space-time, which is curved by the presence of mass. The trampoline represents space-time, the bowling ball is the black hole, and the marble represents any object, even light itself. The closer an object gets to the black hole, the more it is pulled in. The closer you get to the black hole, the steeper the curvature of space-time, and the harder it becomes to escape its gravitational clutches. This immense gravitational pull is what makes black holes some of the most fascinating and mysterious objects in the universe. Now, let's imagine a hypothetical journey towards a black hole. As you approach this cosmic monster, you would feel its gravitational pull becoming increasingly stronger. But this force wouldn't affect all parts of your body equally. If you were falling feet first, your feet would experience a much stronger gravitational pull than your head, simply because they are closer to the black hole. This difference in gravitational force would stretch your body, like a piece of spaghetti being pulled from both ends. This phenomenon, aptly named spaghettification, is a consequence of the extreme tidal forces present near a black hole. Tidal forces arise because gravity's pull weakens with distance. The part of your body closer to the black hole experiences a significantly stronger pull than the part farther away, leading to this unsettling stretching effect. As you plunge deeper into the black hole's gravitational well, the stretching intensifies. Eventually you would cross a boundary known as the event horizon. This is the point of no return, beyond which nothing, not even light, can escape the black hole's gravitational grasp. What happens beyond the event horizon remains one of the biggest mysteries in astrophysics. Our current understanding of physics breaks down at the singularity, the infinitely dense point at the center of a black hole. Here, space and time as we know them cease to exist. Some theories suggest that matter is crushed out of existence at the singularity. Others propose that it could be a gateway to other parts of the universe, or even to other universes altogether. These ideas, while intriguing, remain speculative for now. Section 5. A bridge to another universe? The enigmatic possibility. The concept of black holes as portals to other universes is a tantalizing one. These cosmic giants, with their immense gravitational pull, have fascinated scientists and dreamers alike for decades. Imagine, if you will, that the singularity at the heart of a black hole is not an ending but a beginning, a doorway to a realm governed by different laws of physics. This idea challenges our understanding of the universe and opens up a realm of endless possibilities. This idea stems from the theoretical concept of wormholes. Wormholes are fascinating structures that could, in theory, connect distant points in space and time. Visualize space-time as a sheet of paper. This analogy helps us understand the complex nature of these theoretical constructs. Now fold the paper in half, so that 2 points on opposite sides touch. This simple act of folding represents the bending of space-time. If you could pierce a hole through these points, you would create a shortcut between them. This shortcut is what we refer to as a wormhole. This, in essence, is what a wormhole is thought to be, a tunnel through space-time connecting 2 distant points. Such a tunnel could potentially allow for faster-than-light travel. While there is no observational evidence for their existence, wormholes are theoretically possible within the framework of Einstein's theory of general relativity. This theory, which has stood the test of time, provides a mathematical foundation for the existence of these extraordinary phenomena. Now imagine that the singularity at the heart of a black hole acts as one end of a wormhole. If this were true, then falling into a black hole might not be a death sentence, but a journey through this cosmic shortcut. Where would such a journey lead? Perhaps to another point in our own universe, billions of light years away. Or even more mind-boggling, to a different universe altogether, with its own unique set of physical laws and constants. Of course, this is all highly speculative. The extreme conditions within a black hole make it incredibly challenging, if not impossible, to test these theories directly. However, the very possibility of such cosmic journeys captures the imagination and fuels our desire to understand these enigmatic objects. The existence of black holes also presents us with a fundamental paradox. Quantum mechanics, the theory governing the subatomic world, dictates that information cannot be destroyed, yet when an object falls into a black hole, it seems to vanish from our universe, taking all its information with it. This conundrum is known as the information paradox. One possible solution lies in the concept of Hawking radiation, proposed by physicist Stephen Hawking. This theory suggests that black holes are not entirely black, but emit a faint radiation due to quantum effects near the event horizon. This radiation, however, is thought to be random and not to carry any information about the objects that fell into the black hole. So the information paradox remains a subject of ongoing debate and research in theoretical physics. Despite the many mysteries surrounding black holes, they offer us a unique opportunity to test and refine our understanding of the universe. By studying these extreme environments, we can probe the limits of our current theories of gravity, quantum mechanics, and the nature of space and time itself. Furthermore, the study of black holes has implications for cosmology, the study of the origin and evolution of the universe. Supermassive black holes, millions to billions of times more massive than our Sun, are thought to reside at the centers of most galaxies, including our own Milky Way. Understanding their role in galaxy formation and evolution is a key area of research. Black holes, once considered merely theoretical curiosities, are now recognized as fundamental constituents of our universe. They are cosmic laboratories where the laws of physics are pushed to their extremes, offering us a glimpse into the unknown. While the fate of an object falling into a black hole remains uncertain, the possibilities range from the intriguing to the downright mind-boggling. Spaghettification, journeys through wormholes, gateways to other universes, these are just some of the tantalizing ideas that black holes evoke. As our understanding of these cosmic enigmas continues to evolve, one thing remains certain: the universe is a far stranger and more wondrous place than we could have ever imagined.